Now the fun begins. So, Math 60 loves graphing. So what we're going to look at is graphs of logarithmic functions. So what I'm going to start with is just a reminder that a logarithm is the inverse of an exponential. So the first thing I want you to start with is just graph y equals 2 to the x. So you should be very comfortable with that one by now, right? So we're going to go x, y equals 2 to the x. What values do we choose for x? Well, we choose things like 0, -1, -2, and 1, 2 maybe, right? So we know that when x is 0, 2 to the 0 is 1. 2 to the -1 equals a half. 2 to the -2 is a quarter. I don't know why I started writing these equal signs. 2 to the 1 is equal to 2, and 2 to the 2 is equal to 4. So we'll just have that base graph. So we've got 0, 1, 1, 2, 2, 4, and then approaching that horizontal asymptote. We could even put 3, 8, 6, 7, 8. Sometimes I mess up the scale of these, and I just always want to double check. So this is my y equals 2 to the x base graph, right? And then we did all sorts of transformations on it. Well, we're going to stick with y equals 2 to the x being our base graph, but now we're going to do the inverse. So if you think about that, I'll do it in a different color. Let's pick a fun color, right? If we know that y equals 2 to the x, then the inverse would be x is equal to 2 to the y. So if we were to do a table of values for this, x and y, we could just take all of these points and switch them. So we could say when x is a quarter, y is -2. When x is a half, y is -1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. So I've just swapped all the x and the y values. Now, why is this a logarithmic graph? Well, just to remind you that if you have x is equal to 2 to the y, a logarithm allows you to solve for y. So y equals, it allows you to solve for the variable and the exponent. Y equals log base 2 of x. So x equals 2 to the y is the same as y equals log base 2 of x. So let's think about what the base graph looks like. Well, let's start with when x is 1, I guess. We'll take that, kind of that middle place. When x is 1, we have y equals log to the base 2 of 1. 2 to what exponent is 1? 0. So we have a point 1, 0. For this one here, we've got y equals log to the base 2 of 2. 2 to what exponent is 2? 1. For this one, we have y equals log to the base 2 of 4. So when we put in x is 4, then y would be 2. 2 to the exponent 2 is 4. And then we go towards the other way. So when we say y equals log to the base 2 of a half, 2 to the -1 is a half. So when x is a half, y is -1. And then lastly, when x is a quarter, y is -2. So we get this shape. And we could even put 8, 3 in here if we wanted to. This is y equals log to the base 2 of x, which is the inverse of y equals 2 to the x. Okay. Now, let's just talk for a second about domain, range, and asymptotes. When we're talking about our exponential function is this blue graph. The domain, let's do it a little farther down. We'll just compare the two. Oh, it's not letting me erase. There we go. So the domain of an exponential function is -infinity to infinity. And the range of this exponential function before we do any transformations is round bracket 0 to infinity. Why is it a round bracket at 0? Right? 2 to any exponent cannot equal 0. You have that horizontal asymptote. We have a horizontal asymptote at y is equal to 0. Now let's look at this information for our logarithmic graph. Let's say what's the domain, what's the range, and what's the asymptote? Well, the domain is now what the range of your exponential function was. Now it's 0 to infinity. So this time the domain has been affected. And then when we talk about the range, It's what the domain was, so negative infinity to infinity. And you can see that on the graph, right? So we could never approach x is equal to 0, right? We can't put a 0 in for x, and we also can't put negative values in for x. So log of a negative number does not exist. Log of 0 does not exist. Okay? Whereas the range, our y values, we're going to get everything from negative infinity to infinity. So then what about our asymptote? Well, instead of having a horizontal asymptote, we're going to have a vertical asymptote. And this time it's going to be at x is equal to 0. So the domain and the vertical asymptote are linked in a logarithmic graph, and the range and the horizontal asymptote are linked in an exponential function. So now what we're going to do, as always, right, fun times, is we are going to transform this base logarithmic function. And you could do this using a table of values if you want to, or you can know the shape of this logarithmic graph. So you can know that it has this vertical asymptote at x equals 0. You can know that it has an x-intercept at 1, 0, and then it's got that shape 2, 1, 4, 2, and then 8, 3, right? Potentially. So let's look at some. So let's start off looking at y is equal to log to the base 2 of x minus 3. Thinking about transformations, is this minus 3 going to be a transformation on x or a transformation on y? Well, where is it? Is it in the bracket with x or is it outside of the bracket? It's in the bracket. So I'm going to assume, I'm going to briefly describe how the graph can be obtained, and I'm going to take the original graph and I'm going to shift it right 3. So if you want to take these base points, okay, so if you want to take, sorry, it's not scrolling very nicely. If you want to take these points here in this table of values and just shift them right 3, you don't have to do a table of values. So let's just shrink this down a little bit, right? I could take this point here at 0, 1, or sorry, 1, 0, and I could put it 1, 2, 3, I could put it at 4, 0. This point here at 2, 1, I could put it 5, 1. This point here at 4, 2, I could put it 7, 2. But the biggest thing you're going to notice is that that horizontal asymptote is going to shift. So instead of having a horizontal asymptote at x equals 0, it's now going to be shifted right to x is equal to 3. Sometimes I like to draw the asymptote in because it gives me a guideline. So I know that the graph is going to reach this way. I don't have to be exact about how it reaches. And then it's going to reach this way. And in the long run, we're not going to replicate a ton of logarithmic graphs. They're kind of tricky. But what I want you to understand is that the domain has shifted. The domain of this graph is now going to be 3 to infinity because it's shifted right. The range is not going to change. In fact, they don't even ask you the range. I'm going to write it here, but it only says give the domain and the vertical asymptote. And the domain shifted because the vertical asymptote shifted as well. It is now x is equal to 3. So this is the key information, is that when you have a domain shift, so when you have a horizontal shift, it's going to affect the domain and the vertical asymptote of a logarithmic function. Whereas with an exponential function, it was all about vertical translations that affected the range, right? And the horizontal asymptote. Ugh. Okay, let's talk about how you would graph this if you didn't, want to just take your points and shift them. So let's talk about what this equation would look like. So we're going to choose values of x, and we're going to say y is equal to log to the base 2 of x minus 3. Now you have two choices. You could, you still kind of have to think of it as a shift. So in the last graph, remember we did the center point at 1, 0. We should shift that 3 to 4, 0. But what we're thinking of here is that we're plugging in values of x that when we subtract 3, oh, that's awful, we could take the log of it. So for example, for this one, it would be log base 2 of 1. 2 to the exponent 0 is 1. So let's think about what if we wanted to choose a value for x that's going to allow us to take the log of. So log base 2 of 2 we know is 1. How would we get 2? Well, we do 5 minus 3. So the next x value I would choose would be 5, and that would give me 1. And then I could think about the next one I want to take the log of is 4. So what minus 3 would give me 4? Oh, it's 7. So then that would give me, when x is 7, y is 2, right? But really what I'm doing is taking all of these y values and shifting them right 3. So the next one would be at 3.5, and then this one would be at 3.25, right? And that would give me -1 and -2. But again, when I'm sketching, as soon as I know where that x-intercept is, I kind of just approach the asymptote. The other way of doing it, if you didn't, like if this makes no sense to you doing this table of values, what you could do is change this to exponential form. So you could say this is 2 to the y is equal to x minus 3. So the base stays the base. 2 to the exponent y is equal to x minus 3. And you could say 2 to the y plus 3 is equal to x. And then you could choose values of y. Like you could choose 0, -1, -2, 1, and 2, and then solve for x, right? So you can kind of do the table of values backwards. Kind of up to you. All right, let's look at this next one. In this next one, I want to really focus on describing those transformations. I want to talk about what's going to happen. Is there going to be any horizontal shifts or potentially reflections? So what I do is I take this. This is my restriction on my domain. I know two things. I know that this cannot equal 0, right? 3 minus x cannot equal 0. Just like for this one, x minus 3 could not equal 0. So x could not equal 3. That's what gave us our vertical asymptote. Our vertical asymptote came because we couldn't take the log of 0. So for this one, I'm just going to add the x, and I'm going to say again that x cannot equal 3. So I'm going to say that my vertical asymptote for this guy is still x cannot equal 3. But what about my domain? My domain comes, just like this one, is that I had to take the log of a positive number. So for my domain, the x minus 3 had to be greater than 0. X had to be greater than 3. Huh, interesting. So I didn't even really need to graph it to know this. For this one, I would say that 3 minus x also has to be greater than 0. I can't take the log of a negative number. So if I add x to both sides, I end up with that x has to be less than 3. So the domain is going to be x has to be less than 3. So it's going to be 3 to negative infinity. Now I know this even without thinking about transformations. Okay, so the first one I did with transformations, I was like, okay, I shifted right 3. That moved my vertical asymptote, that moved my domain. For this one, I'm kind of going backwards. I'm saying, hey, let's figure out vertical asymptote and domain first. The vertical asymptote comes because you can't take the log of 0. So 3 minus x cannot equal 0. The domain comes because you can't take the log of a negative number. So 3 minus x has to be greater than 0, so x has to be less than 3. Let's talk about this from in terms of a transformation. What is going on in this graph? Well, there's two ways of looking at this. I personally, and this is just my stubbornness, I personally would write this as negative x plus 3. I want to see it like our normal transformation is a f of b x minus c plus d, right? So I want to write this as x minus c. Then I notice that I can't have this negative in front, so I'm going to factor that out. So for me, I'm going to say that my transformations are, number one, it's going to be a reflection in the x values over the y-axis. And then I'm going to say that it's moved right 3. So if you think about that, right, if we take this base graph, this purple graph, actually, let me just open Desmos, so that'll make things easier. Okay, so this is my y equals log base 2 of x. What I'm saying for my transformations is the first thing it's going to do is it's going to reflect in the x values over the y-axis. So I'm going to have y equals log base 2 of negative x. And that's going to be a reflection. And then I'm going to move it right 3. So my next line will say y equals log base 2 of negative bracket x minus 3. So that's going to be this green graph. It's my graph that's been reflected over the y-axis and then been shifted to the right 3. Can you see that this green graph is my final graph? It has a vertical asymptote at x equals 3, and the domain is that x is all values less than 3. Great. Okay, that is what this graph is going to look like. So for me, what I would do is I would take those key points and I would say, okay, I'm going to reflect them over the y-axis and then I'm going to move them right 3. So what's going to happen is you're going to have this point here. I should do this in a different color. I should have done this on 2 different graphs. Just thinking about that. Oh, whatever. Okay, so I was like, oh, should I just pause the video and redo this? Nah, it's fine. Okay, so it's been reflected and then moved to the right 3. Okay, this point here at 2, 1 has been reflected and then moved right 1, 2, 3. And then this point at 4, 2 has been reflected and then moved right 3. So this is going to be my shape. Some people know it as like from the asymptote, you can go like up 1 and then over 1 up 2, over 2 and up 4, over 3 and up 8, or over 8. 1, 2, 3, 5. And then I'm going to approach the asymptote. This is my sketch. And I will not on the test ask you to graph a logarithmic graph from hand by hand. That's why I'm like kind of doing this in like not the perfect way. I'm not exactly expecting you guys to be able to replicate log graphs. I would like you to recognize, right? Can you recognize that this graph has been reflected and moved right? Awesome. Okay. What I want to know for sure is that you can identify that this one would have a vertical asymptote at x equals 3 and that the domain would be x is less than 3. Whereas for the first one, it had the same vertical asymptote, but the domain was x was greater than 3 because there was no reflection of the x values over the y-axis, and also because when you set the of greater than 0, you just ended up with x is greater than 3, whereas for this one, you ended up with x is less than 3. If you wanted to do a table of values for this one, you totally could. What I would probably do is go back to the point system. Do you remember way back when we first learned how to transform graphs? So I would take my points at a quarter, a quarter and 2, -2, a half and -1, 1 and 0, 2 and 1 and 4 and 2. And then I would do the things. So I would times the x values by -1, and then I would add 3 to the, and then I would add 3, right? So I would times by -1. This is writing horribly. Let me just zoom in. Times by -1, add 3, times by -1, add 3, times by -1, add 3, and times by -1 and add 3. Oof, so that's going to be -0.25 plus 3. So this one's going to be at 2.75 and -2. This point here would be at 2.5 and -1. This point here would be at -1 plus 2 is, -1 plus 3 is 2 and 0. This point here would be at -2 plus 3 is 1 and 1. And then lastly, this point here would be at -1 and 2. So you could do it as a transformation of points if you just want to pull those key points off of your y equals log to base 2 of x graph. And again, I won't ask you anything other than a log base 2 graph so that you can get really comfortable with these key points. And then the last thing before we go on to the next page, I just have to point out is that this is not the way the textbook does it. The textbook, if it was describing the transformations, would say, first of all, it's a shift left 3, and then it's a reflection over the y-axis. And that's totally fine. Okay, we talked about this a lot with the exponential functions. So if you want to look at it from left to right, this is a +3, which is going to make it go left, and then the -x is going to make it reflect. I don't personally enjoy that. I like making everything the same. When we go back to chapter 6 and we graphed, or when we go forward to chapter 6 and we graph, um, I've lost my word. What's the word? Trig, right? We're going to be going back to this idea. So this is the only chapter they switch and they go, hey, you could go left and then reflect instead of reflect and then right. It does the same thing if I show you on Desmos, right? So let's just hide these. So what they do is they say, take your base graph of y equals log to the base 2 of x, and then the first thing you're going to do is go left. So they say graph y equals log base 2 of x in brackets plus 2. So they make it go left, and then they take that and they reflect it. And when it reflects, okay, I actually can't show it with this. I have to show that they have to reflect it. This is why I don't like it, because you can't actually show the step by step in Desmos. Once you go left, oh, sorry, 3, and then you reflect it, you're going to end up with this other graph. So if I put this one on here, see, look at the black graph and the green graph. They are reflections of each other over the y-axis. So I don't know if you can kind of see this. They have that invariant point here where they cross negative 2, 0 versus 2, 0, and so on and so forth. So it doesn't matter whether you reflect and then go right or go left and then reflect. The textbook likes reflect and then go left. I disagree. I would say reflect and then go right. But they will both get you to the same place. Awesome. I hope this is making sense. This is feeling like a little bit of like a bah, but let's try one more. So let's look at this guy here. So if I was going to graph y equals negative log to the base 2 of x plus 2. First thing I want to ask you is domain and vertical asymptote, because that's where we're going to go to. So for this one, what's the domain? Well, the domain comes from here. Though you can't take the log of a negative number, so x has to be greater than 0. Well, that's okay. That's normal. 0 to infinity. And the vertical asymptote comes because this x cannot equal 0. Well, that's okay. That means that my vertical asymptote is x equals 0. So if I wanted to put this on here, I could picture that this graph is going to have a vertical asymptote at x is equal to 0, and my domain is going to go to the right. Cool. So because there was no transformations on x, there was nothing to affect the domain or the vertical asymptote. What would this graph look like? Well, if I was to describe it, the first thing I would say that it is reflect the y values over the x-axis, and then it's going to be a vertical shift up 2. So we could just take those points. I feel like that's the easiest way to do this. We had that point at, not negative a quarter, we had a point at a quarter and negative 2. We had a point at a half and negative 1. We had a point at 1 and 0. We had a point at, I'm going to forget these other ones, 2 and 1. And we have a point at 4 and 2. We are going to reflect the y values over the x-axis. We're going to times all the y values by negative 1. And then we're going to move them all up 2. Now you could do this in 2 steps if you want, right? You could multiply all the y values by negative 1, get an answer, and then add 2. That's probably the safer way to do it. I just decided to go hard. So this point would be at a quarter. And then negative 2 times negative 1 is positive 2, plus 2 is 4. This point here is going to be at a half. Negative 1 times negative 1 is 1, plus 2 is 3. This point is going to be at 1, and then 0 times negative 1 is still 0, plus 2 is 2. And then this point is going to be at 2, and negative 1 plus 2 is 1. And then this point here is going to be at negative 2 plus 2 is 0. So just simply going off of here, we're going to have a quarter and 4. We're going to have a half and 3. We're going to have 1 and 2, 2 and 1, and 4 and 0. So what's going on here? Well, the graph's been flipped. right? So instead of going down towards the asymptote, it's going up towards the asymptote, and then it's going this way. And then if we wanted to, we could add that other point at 8. Just to keep mine looking a bit good. So this is the graph, but again, do I need it? No. Before I even graphed it, I knew that the domain was 0 to infinity, and I knew that it had a vertical asymptote at x is equal to 0, right? Because there's no transformations on x. So good to be able to recognize it. Like I want you to be able to recognize that this is the y equals log to base 2 of x shape. It's been reflected in the y values over the x-axis and it's been moved up too. But I'm not super concerned about you being able to replicate these. What I want you to be able to do is this. If I asked you for the asymptote of any logarithmic graph, normally it's at x is equal to 0. What transformations will change it? What transformations could affect the asymptote? Did moving it up affect it? No. Did a y transformation affect it? No. Really, it's moving it left and right. Those are the only two things that will affect your asymptote. So what I want you to look at is that the transform graph, like how do I want to write this? So what I want it to be is that whatever's in the bracket with the log, so let's just write if y is equal to log base 2 of x minus c, then the asymptote is at x is equal to c. So you're going to take whatever is in the of and set it equal to 0 and solve for x. Same thing for the domain. Normally the domain is 0 to infinity. The things that will affect the domain is going left and right. So if we think about transform graph being y equals log to base 2 of x minus c, then you would say that x minus c has to be greater than 0. So x has to be greater than c. Okay, so it's going to be c to infinity. Unless you also have a reflection in the y values. So if you take your x values and reflect them over the not y values, y axis, I should say over y axis. So if you have something like c minus x, then you're going to end up with x being less than c, and so it's going to go negative infinity to c. Right? The range, negative infinity to infinity, nothing's going to affect it. And then if they ever do ask you the x-intercept, right, the x-intercept is 1, 0. To find the x-intercept, lots of things are going to change the x-intercept, so I'm always going to say, like everything does. Whoa, that was not a good everything. And then you're just going to say that to find the x-intercept, let y equal to 0 and solve for x. So finishing up this extremely long video, I'm really sorry for this, I should make it shorter, is that we're just going to do 3 examples where you're just going to tell me vertical asymptote and domain. Okay, so to find the vertical asymptote, you set the log of equal to 0. So for this one, it's going to have a vertical asymptote at x equals negative 2. To find the domain, you're going to set the of that it has to be greater than 0. So x has to be greater than negative 2 or negative 2 to infinity. Okay, that's kind of the takeaway. Yeah, we had to go through some awful graphing to get there, but this is the takeaway. You do not need to graph to determine vertical asymptote and domain. Okay, so for this one, what about the vertical asymptote? This is the of. The plus 4 is not in brackets, so it's going to be that x is equal to 0, and your domain is going to be that x has to be greater than 0, which is 0 to infinity. Okay, last one here. If I wanted to find the vertical asymptote, 6 minus x cannot equal 0. So to find the vertical asymptote, you let it equal to 0, and you'd say that x is equal to 6, right? So the vertical asymptote would be x is equal to 6. And then if I was setting my domain, I'm going to say that that 6 minus x has to be greater than 0. So x has to be less than 6 or negative infinity to 6. Hopefully that makes sense. There is a worksheet for you to practice because I just felt like you're more apt to graph if you're given a space to graph. And then I wanted to ask these little tiny specific questions where you don't need to graph, but you could still tell me vertical asymptote and domain. Good luck. Sorry for the length.